Hello, everyone. Can you hear me? Let me change to full screen. So, last stream, I read about locked data structures. Basically, they were talking about heaps and linked lists and hash tables, but with the locks in the concurrent version of them. This chapter is about condition variables. Thus far, we have developed the notion of a lock and seen how one can be properly built with the right combination of hardware and OS support. Unfortunately, locks are not the only primitives that are needed to be built in concurrent programs. In particular, there are many cases where a thread wishes to check whether a condition is true before continuing its execution. For example, a parent thread might wish to check whether a child thread has completed before continuing. This is often called a join. How should such a way to be implemented? Let's look at figure 30.1. So void child, we have, okay, appointed to a void. We have printf child. How do we indicate we are done? And then return null. And then in main begin, we have a C thread. Create the thread, C null, child null. How do we wait for the child? Oh, we already looked at this. It's basically join. What we would like to see here is the following output. Begin, child, parent. We could try using a shared variable as you see in figure 30.2. This solution will generally work, but it's hugely inefficient as the parent spends and wastes CPU time. What we would like here instead is some way to put the parent to sleep until the condition we are waiting for comes true. So volatile int done is 0. We have a child done is equal to 1. While done is 0. What did volatile mean again? Wait. Volatile meaning C. Uh, okay, it's saying that the value can change. So it prevents the compiler from doing certain optimizations. Volatile tells the compiler not to optimize anything that has to do with the volatile variable. Volatile, a variable is said to be volatile if its value can be read or modified asynchronously by something other than the current thread of execution. Okay. Also, hold on. Also, let's see what they have here. Condition variable. Good examples from condition variable chapter. Will by making type run the resulting executable to see how it works. Insert sleep calls or various length to control timing and force bad things to happen. Okay. In multi-threaded programs, it is often useful for a thread to wait for some condition to become true before proceeding. The simple approach is of just spinning until the condition becomes true is grossly inefficient and wastes CPU cycles, and in some case can be incorrect. So definitions and routines. To wait for a condition to be true, a thread can make use of what is known as a condition variable. A condition variable is an explicit cue that threads can put themselves on when some state of execution is not as desired. By waiting on the condition. Some other thread, when it changes the set state, can then wake one of those waiting threads and thus allow them to continue. The idea goes back to Dijkstra. The idea goes back to Dijkstra's use of private semaphores. A similar idea was later named a condition variable by Hoare in his work on monitors. To declare such a condition variable, one simply writes something like this. So thread condition C, which declares C as a condition variable. A condition variable has two operations associated with it, wait and signal. The wait call is executed when the thread wishes to put itself to sleep. The signal call is executed when a thread has changed something in the program and thus wants to wake up a sleeping thread waiting on this condition. Specifically, the POSIX call looks like this. So we have wait, condition, mutex, and then we have a signal. So mutex, condition, mutex lock, wait, child, printf child, uh, thread exit, return null, and thread exit is mutex lock, m, then is 1, and then we do the signal, and then we unlock. Printf parent begin, pthread pthread create. Okay, create the child thread and assign it to p. We are doing thread join, and thread join is you're locking, right? While done is 0, condition wait. Now, and then we mutex unlock. Now printf parent end. The wait call is executed when a thread wishes to put itself to sleep. The signal call is executed when a thread has changed something in the program and thus wants to wake a sleeping thread waiting on this condition. We often refer to these as wait and signal for simplicity. One thing you might notice about the wait call is that it also takes a mutex as a parameter. It assumes that this mutex is locked when wait is called. The responsibility of wait is to release the lock and put the calling thread to sleep atomically. The responsibility of wait is to release the lock and put the calling thread to sleep. So this puts the main thread to sleep. But what about, what do you mean release the lock? So this wait condition unlocks this, I'm assuming. No, but that's what this function does. When the thread wakes up after some other thread has signaled it, it must require the lock before returning to the caller. This complexity stems from the desire to prevent certain race conditions from occurring when a thread is trying to put itself to sleep. Oh, I see. So this over here unlocks this thread. This unlocks this thread. And when the CPU goes back to this, it locks it again. Like when the condition is met, it locks it again. There are two cases to consider. In the first, the parent creates the child thread but continues running itself and thus immediately calls into thread join to wait for the child thread to complete. In this case, it will acquire the lock. Check if the child is done. It is not put itself to sleep by calling wait. The child will eventually run, print the message child, and call thread exit to wake the parent thread. This code just grabs the lock, sets the state variable done, and signals the parent, thus waking it. Finally, the parent will run, unlock the lock, and print the final message parent end. Okay, let me reread this. There are two cases to consider. In the first, the parent creates the child. The parent creates the child thread but continues running itself. Assume we have only a single process and thus immediately calls thread join to wait for the child thread to complete. So this runs create and then the run thread join. Wait for it to complete. This case, if they look out the log, check if the child is done. It is not. Put itself to sleep by calling wait. Okay. So it lock put itself to sleep. The child will eventually run, print the message child, and call thread exit. So child, print child, thread exit. Then we have another, but the condition wait unlocks it, right? Thread exit prints the message child and call thread exit to wake the parent thread. This code just grabs the lock, sets the state variable done, and signals the parent, thus waking it. Finally, the parent will run, returning from wait with the lock held, unlocking the lock, and print the final message. Okay. So it will return from here, unlock, and then finally print parent. In the second case, the child runs immediately upon creation, sets done to 1. Okay, so the CPU is like executing this, executing this, executing this, executing this, and then it switches to the other thread. The other thread will print f child, and then set the done to 1, call signal to wake the a sleeping thread, but there is none, so it just returns and is done. Right. The main thread did not reach thread join, but the child thread, it sent out the signal, unlock the lock, and yeah, and then it returns now. Sets done to 1, call signal to wake a sleeping thread, and is done. The parent then runs, calls thread join, sees that done is 1, and thus does not wait and returns. Thread join, and lock, but done is 1, so this does not execute, so no waiting, so it unlocks. Does the context switch ever happens during this part? Like there's a CPU, like when it's waiting, does the CPU come back here if the condition is not met and waste CPU cycle? One last note, you might observe the parent uses a while loop instead of just an if when describing whether to wait on a condition. While this does not seem strictly necessary per logic of the program, it is always a good idea, as we will see below. To make sure you understand the importance of each piece of the exit and join code, let's try a few alternate implementations. First, you might be wondering if we need the state variable done. Why did the code look like the example below? Figure 30.4. So exit is like this. So lock, signal, unlock, and then join is like this. Lock, wait, unlock. Okay, but if the child executes first, and then this entire thing is already executed, and then the parent execute next, so it locks and then it waits, but the signal is already sent. It's not going to be sent again. So the parent will be stuck here, right? In this case, the child will send a signal, but there is no thread asleep on the condition. When the parent run, it will simply call wait and be stuck. No thread will ever wake it. On this example, you should appreciate the importance of the state variable done. Because the value of the thread the threads records the value the threads are interested in knowing. Sleeping, waking, and locking are built around it. Here in 30.5 is another poor implementation. In this example, we imagine that one does not need to hold a lock in order to signal and wait. What problem could occur here? Think about it. So let's see. Done one. The CPU switches to main thread. Uh, like let's say the parent creates, sorry, the main thread creates a child thread, and then the CPU switches to the child. All of this executes. Done is one, and code it sends the signal. Then when it goes back to the main thread, goes to join, this will be false, so the wait will not execute and it will end with no errors. There might be some other issue then. Okay, let's see. Okay, I think during the main thread, it prints, creates the child thread, goes to join, and then in join, it checks if done is equal to 0, which it is. And then right after this execution, it goes to the CPU switches to the child thread, and then the child thread, child thread does printf, and then thread exit does is equal to 1, and then it signals this. If it signals this, it goes back to the parent child, it waits, but the signal has already been sent, so it will be stuck waiting. That's what I think would be the issue. Like the wait has to be encountered first and then signal second. But if it checks for done, switches, and then the signal is sent, and then switches back, and then the wait is doing next, it's going to be waiting forever because the signal was sent previously. That's what I think would happen. Issue here is the subtle race condition. Specifically, if the parent calls thread join and then checks for the value of done, it will see that it is 0 and thus try to go to sleep. Just before it calls wait to go to sleep, the parent is interrupted and the child runs. The child changes the state variable down to 1 and signals, but no thread is waiting, and thus no thread is woken. When the parent runs again, it sleeps forever, which is hard. Hopefully, from this simple join example, you can see some of the basic requirements of using condition variables properly. To make sure you understand, we now go through a more complicated example, the producer-consumer or bounded buffer problem. Although it is strictly not necessary in all cases, it is likely simplest and best to hold the lock by signaling when using condition variables. The example above shows a case where you must hold the lock for correctness. However, there are some other cases where it is likely okay not to, but probably is something you should avoid. Thus, for simplicity, hold the lock when calling signal. Converse of this tip, hold the lock when calling wait, is not just a tip but rather mandated by the semantics of wait. Because wait always assumes a lock is held when you call it. releases said lock when putting the caller to sleep. Reacquires the lock just before returning. Thus, generalization of the step is correct. Hold the lock when calling signal or wait. Now that this example is not real code because the call to wait always requires a mutex as well as a condition variable. We just pretend that the interface does not do so for the sake of the negative example. Okay. So wait over here needs a condition and mutex. But for this example, they remove the mutex. The producer consumer bounded buffer problem. The next synchronization problem we will confront in this chapter is known as the producer consumer problem, or sometimes as the bounded buffer problem. Buffer count is 0. So put and get, which was first posed by Dijkstra. Indeed, it was this very producer consumer problem that led Dijkstra and his co workers to invent the generalized semaphore, uh, which can be used as either a lock or a condition variable. We will learn more about semaphores later. Imagine one or more producer threads and one or more consumer threads. Producers generate data item and producers generate data items and place them in a buffer. Consumers grab said items and from the buffer and consume them in some way. So producer, imagine one or more producer threads and one or more consumer threads. Producers generate data items and place them in a buffer. Consumers grab the said item from the buffer and consume them in some way. So is it like a stack? Is the buffer like a stack? Is it like a queue? This arrangement occurs in many real systems. For example, in a multi-threaded web server, producer puts HTTP request into work queue. The bounded buffer, the consumer thread takes request out of this queue and processes them. A bounded buffer is also used when you pipe the output of one program into another. So grep foo file.txt. So we are searching for foo in a file.txt and pipe. We are doing a word count and we want a long list. We want long answer. This example runs two process concurrently. Grep writes lines from file.txt with the string foo in them to what it thinks is standard output. The Unix shell redirects the output to what is called Unix pipe, created by the pipe system call. The other end of this pipe is connected to the standard input of the process called WC. It simply counts the number of lines in the um, input stream and prints out the result. Thus, grep process is the producer and WC is the word count process is the consumer. Between them is an internal bounded buffer. You in this example are just a happy user. This is not concurrent, right? It says this example runs two processes concurrently. Isn't it sequential? Isn't it more like this runs first and after this finishes, then using the output of this one, we are running this. So this runs after this. That's as concurrent. And because the bounded buffer is a shared resource, we must, of course, require synchronized access to it, lest a risk condition arises. To begin to understand this problem better, let us examine some actual code. The first thing we need is a shared buffer into which a producer puts data and out of which a consumer takes data. Let's use a single integer for simplicity. You can certainly imagine placing a pointer to a data structure into the slot instead. and two inner routines to put a value into the shade buffer and to get a value out of the buffer. See figure 30.6 for details. So buffer counter, but um, we have value. We put that in the buffer. Count as one. We assert count as one. We make it zero and return buffer. Shouldn't buffer be like a list, like a queue? No, buffer is a queue, right? Why is it like one value? What even is the point of count? Uh, the two routines to put a value into a shade buffer and to get a value out of the buffer. It's figure 30.6 for details. It is simple. Now the put routine assumes the buffer is empty and then simply puts a value into the shade buffer, marks it full by setting count to 1. The get routine does the opposite, setting the buffer to empty and returning the value. Don't worry that this shade buffer has just a single entry. Later we will generalize it to a queue. Now we will write some routines that know when it is okay to access the buffer to either put data into it or get data out of it. Conditions for this should be obvious. Only put data into the buffer when count is 0 and only get data from the buffer when count is 1. If we write the synchronization code such that a producer puts data into a full buffer, consumer code from an empty one, we have done something wrong. And in this code, an assertion will fire. This work is going to be done by two types of threads, one set of which we will call the producer threads, and the other set which we will call consumer threads. Figure 30.7 shows the code for a producer that puts an integer into a shade buffer loops a number of times, and a consumer that gets the data out of the shade buffer, each time printing out the data item it pulled from the shade buffer. So producer wide arg, we have I, we have blue. Did we come across 30.7? Okay. So we have producer threads and we have consumer threads. Producer I, we have loops, int arg for I0, we put I. Consumer while 1, int temp get printf temp. Why do we need the arg input in consumer? Buffer only has a single entry. So when we are running this loops amount of time, we are just rewriting buffer. Now imagine that we have just a single producer and a single consumer. Obviously, the put and get routines have critical sections within them as put updates the buffer and get reads from it. However, putting a lock around the code doesn't work. We need something more. Why doesn't putting a lock work? Seems intuitive though. Um, Not surprisingly, that something more is condition variables. In this broken first try, we have a single condition variable condition and associated lock mutex. So we lock. If count is 1, we wait. So we have loops, must initialize somewhere. We have the condition, we have the mutex. So first we lock it. And then if the condition is 1, then we wait. Let's assume the condition is 0. So we put I, we signal, the condition, and then we unlock. Now we are checking the count is 1 of the condition. So uh, locking it with mutex. If count is 1, then we wait. Otherwise, if it goes back to 0, then we put it here. We put it back into the buffer and we update the count to 1. Let's examine the signaling logic between producers and consumer. When a producer wants to fill the buffer, it waits for it to be empty. P1 to P3. P1 to P3. The consumer has the exact same logic but waits for a different condition, fullness. Consumer C1, C2, C3. Now temp we get, right? And then we have the condition. We get it. We signal the condition. We unlock it. So wait, if the producer puts something, it signals the condition and it will wake this line up. But if the consumer condition signal, if the consumer signals with this condition, it then it will wake the thread over here. Yeah, I think I understand. With just a single producer and a single consumer, the code in figure 30.8 works. However, if you want more than one of these threads, the solution has two critical problems. If we have more than one of these threads, we have single producer thread, single consumer thread, then it works. But with multiple of these, what is the issue? If we have multiple producer threads, they're all going to be no, but this is locked, right? No, but the condition where it will unlock it. So the other producer thread will also be waiting. And when, let's say there's one consumer thread, when the one consumer thread signals it, only one of the producer threads will work. The other producer thread might wait indefinitely. Let's understand the first problem, which has to do with the if statement before the wait. Assume there are two consumers, TC1 and TC2, and one producer, TP. First, a consumer runs, requires the lock, check if any buffers are ready for consumption, finding that none, waits, which releases the lock. So we are talking about TC1, which goes through the entire thing and ends up in wait. Then the producer runs, it acquires the lock, checks if all buffers are full, and finding that not to be the case, and goes ahead and fills the buffer P4, and then the signal. Critically, this moves the first consumer from sleeping on the condition variable to the ready queue. TC1 is now able to run, but not running yet. Producer then continues until realizing the buffer is full, at which point it sleeps. So, okay, it unlocks and it goes back here and then it goes back to wait. Okay. So loops is like how many times you want to input into the buffer, right? Like how many times you're using the buffer. So this cycle will work loop times. So you're inputting into the buffer loop times. The Here is where the problem occurs. Another consumer, TC2, sneaks in and consumes the existing value in the buffer. Now assume TC1 runs just before returning from wait. It requires the lock and then returns. So TC1 was initially here. The CPU switches to the producer. Producer fully runs, like it signals and then goes back to the second iteration and then goes to wait. And then the CPU switches to consumer 2. Consumer 2 also fully runs. Like it skips this because the count is 1. It varies the count set to 1. Okay, so it skips this, gets the value, signals, and then goes to loops, and then goes back to wait. Sneaks in and consumes the one existing value in the buffer. Now assume, so say 1, 2, 3, 4, 5, 6, skipping the wait at C3 because the buffer is full. Okay, 1, 2, skip this, 3, 4, 5, 6, and then go back to the second iteration. So TC1 is also waiting, right? Sorry, TC2 is also waiting, right? Now assume TC1 runs just before returning from wait. It requires the lock and then returns. It then calls get C4. But there are no buffers to consume. An assertion triggers and the code has no functions, has not functioned as desired. Clearly, we should have somehow prevented TC1 from trying to consume because TC2 snuck in, consumed the one value in the buffer that has been produced. Figure 30.9 shows the actions each thread takes as well as the scheduler state over time. So run, sleep. TC2 is ready all the way. So TC1, if you go back to TC1, it then calls get, there are no buffers to consume. Assertion triggers on the code has not functioned as desired. So it runs get, going back up to get, and assertion occurs. So this causes an error. Problem arises for a simple reason. After the producer woke TC1 and before TC1 ever ran, state of the bounded buffer changed, signaling a thread only wakes them up. It is thus a hint that the state of the world has changed. But there's no guarantee that when the woken thread runs, the state will be still will still be as desired. This interpretation of what a signal means is often referred to as mesosemantics. After the first research that built a condition variable in such a manner, the contrast referred to as Hoare semantics is harder to build but provides a stronger guarantee that the woken thread will immediately learn immediately upon being woken. Virtually every system ever built employs mesosemantics. So condition mutex. We lock, we wait, put, signal, unlock. Is the producer the same? Instead, we have a while loop instead. Oh, so in when it goes out of the wait condition, we are rechecking this again. I see, I see. That's why while is better. Better but still broken while not if. Fortunately, this fix is easy. Change the if to a while. Think about why this works. Now consumers see TC1 wakes up and immediately rechecks the state of the shared variable. The buffer is empty at that point. The consumer which simply goes back to sleep. The corollary if is also changed to a while in the producer. Thanks to mesosemantics, a simple rule to remember with condition variables is to always use while loops. Sometimes you don't have to recheck the condition, but it is always safe to do so. Just do it and be happy. However, this code still has a bug. The second of the two problem mentioned above. Can you see it? It has to do something with the fact that there is only one condition variable. Try to figure out what the problem is before reading ahead. So, what was the second problem again? However, if we have more than one of these threads, the solution has two critical problems. What are they? Let's understand the first. Now, what's the second? Maybe it's the final iteration. Like if we are done, if we want to use this loop some amount of times. But let's say in the last loop, we send a signal and we are done, and both the threads are in waiting. One of the threads will go out of wait, get the thing, and then be done. No, and then it will go back, right? It will be done or it may go back, but the second thread will be waiting forever. I think that's the other issue they're talking about. Let's confirm you figured it out correctly, or perhaps let's confirm that you are now awake and reading this part of the book. Problem occurs when two consumers run first, and both go to sleep. Then the producer run puts a value in the buffer and wakes one of the consumer. Producer loops back and tries to put more data into the buffer because the buffer is full. Producer instead waits on the condition. Now the consumer is ready to run and through two threads are sleeping on a condition. We are about to cause a problem. The consumer C1 then wakes up by returning wait, rechecks the condition and finding the buffer is full, consuming the value. This consumer then critically signals on the condition, waking only one thread that is sleeping. However, which thread should it wake? Oh, when TC1 sends a signal, right? Is it sending a signal to this wait for TC2 or this wait on the producer? But what about the problem I pointed out? What's the solution for that? Because the consumer has emptied the buffer, it clearly should wake the producer. However, if it wakes the consumer TC2 pass, which is definitely possible depending on how the wait queue is managed, we have a problem. Specifically, the consumer TC2 will wake up and find the buffer empty and go back to sleep. The producer, which has a value to put in the buffer, is left sleeping. Yet the consumer thread also goes back to sleep. All three threads are left sleeping. Signaling is clearly needed, but must be more direct. A consumer should not wake other consumers, only producers, and vice versa. Maybe the signal and the weight should be different. Like instead of having condition over here, right? You can have a consumer condition which wakes this. You can have like, let's say, variable CC, and then put a variable CC here. And then for the signal, put a variable PC. So producer condition, and then wait producer condition over here. Maybe that can be a solution. The single buffer producer consumer solution. Figure 30. Okay. Solution here once again is small one. Use two condition variables instead of one in order to properly signal which type of thread should wake up. In the code, producer threads wait on the condition empty and signals fill. Conversely, consumer threads wait on fill and signal empty. By doing so, the second problem above is avoided by design. A consumer can never accidentally wake up a consumer. Producer can never accidentally wake up a producer. Let's see. Now figure 30.13. Figure 30.12 shows the resulting code. So now we have empty and we have fill. We have two condition variables. When checking for a condition in a multi-threaded program, using a while loop is always correct. Using an if statement might be, depending on the semantics of signaling. Using while condition around conditional checks also handles the case where spurious wake-ups occur. In some thread packages, due to details of the implementation, it is possible that two threads get woken up, though just a single signal has taken place. Spurious wake ups are further reasons to recheck the condition on it to recheck the condition a thread is waiting on. We now have a working producer consumer solution, albeit not a fully general one. The last change we make is to enable more concurrency with efficiency. Specifically, we add more buffer slots so that multiple values can be produced before sleeping. Similarly, multiple values can be consumed before sleeping. With just single producer and consumer, this approach is more efficient as it reduces context switches. With multiple producers or consumers, even allows concurrent producing or consuming to take place, thus increasing concurrency. Fortunately, is a small change from our current solution. First change for this correct solution is within the buffer structure itself and the corresponding put and get. We also slightly change the conditions that producers and consumers check in or check in or wait. We also slightly change the conditions that producers and consumers check in order to determine whether to sleep or not. We also show the correct waiting and signaling logic. A producer only sleeps if all buffers are currently filled. Similarly, a consumer only sleeps if all buffers are currently empty. And thus we solve the producer consumer problem. Time to sit back and drink a cold one. So they said figure 30.13. So buffer max, fill pointer, use pointer, count. So put a value in, increment the fill pointer, or they're doing modulus and count plus plus. Get get the buffer, increment the use pointer, count minus minus. Now we have empty fill. We have almost the same thing, but count is max. Why do we have this for loop? Shouldn't it be? So we are only inputting loops number of times. Like after loops number of times, we are never using the producer function ever again. No, no, I mean sorry. Like after the loops amount of times, we can only use the producer with I forgot what I was saying. So we are putting integers from 0 to loops in the buffer. And then we are and then what? And then we are taking out those integers here. I don't get the for loop though. I think they mentioned this work is going to be done by two types of threads. One set of which we will call the producer threads, and the other set which we will call the consumer threads. Figure 30.7 shows the code for the producer that puts integer into a shade buffer, loops number of times. Consumer that gets the data out of that shade buffer, each time printing out the data. So we will now look at one more example of how condition variables can be used. This code study is drawn from Lapson and Reddell's paper on Pilot, the same group who first implemented the MESA semantics described above. The problem they ran into is best shown by a simple example, in this case, in a simple multi-threaded memory allocation library. Figure 30.15 shows a code snippet which demonstrates the issue. As you might see in the code, when the thread calls into the memory allocation code, it might have to wait in order for more memory to become free. Covering condition, an example. How many bytes of the heap are free? Need log in condition 2. Pointer, bytes left, size, mutex, unlock. Problem they ran into is best shown via simple example. This case, in a simple multi-threaded memory allocation library. Figure 30.15 shows a code snippet which demonstrates this issue. As you might see in the code, when a thread calls into memory allocation code, it might have to wait in order for memory to become free. Conversely, when a thread frees memory, it signals that more memory is free. However, code has a problem. Which waiting thread should be woken up? So lock, wait, so allocate memory. So, and then when it frees, whom to signal? You signal here, right? I don't know. I don't get the issue. It's a simple multi-threaded memory allocation library. But I don't understand what the issue is. Which waiting thread should be woken up? I mean, it can be any. Like, do we need a specific thread? We just need some memory, right? Like any memory. Bytes left, pointer, get memory from heap, and get pointer. Consider the following scenario. Assume there are 0 bytes free. Thread A calls allocate 100, followed by thread B, which asks for less memory by calling allocate 10. Both A and B thus wait on the condition and go to sleep. While bytes left is less than size. Wait, so what is size? Bytes left is the max heap size. So what's the max heap size? Thus, A and B thus wait on a condition and go to sleep. Why would they go to sleep? What's the byte left? What's the max heap size? So we have so first there was 100. So we subtract 100 and then we subtracted 10. But assume like we don't have enough space, so they go to sleep. There aren't enough free bytes to satisfy either of these requests. Okay, so let's say the remaining bytes left is like 5. So both 110 will go to sleep. At that point, assume a third thread, consumer C, calls free 50. Unfortunately, when it calls signal to wake a waiting thread, so free pointer size bytes left plus size. So what's this pointer used for? Fortunately, when it calls signal to wake a waiting thread, it might not wake the correct waiting thread, B, which is waiting for only 10 bytes to be freed. A should remain waiting as not enough memory is yet free. Thus, the code in the figure does not work as the threads waking other threads does not know which thread to wake up. It wants to wake up the 10 byte one and not the 100 byte. Two solutions suggested by Lamson and Riedel is straightforward. Replace thread condition signal call in the code above with a call condition broadcast, which wakes up all the waiting thread. By doing so, we guarantee that any threads that should be woken are we guarantee that any threads that should be woken are. The downside, of course, can be the negative performance impact, as we might needlessly wake up many other waiting threads that shouldn't yet be awake. Those threads will simply wake up, recheck the condition, and then immediately go back to sleep. Oh, I see. So bytes left, we add. There are a lot more bytes left. We wake both 10 and 110, but only 100 will go back to sleep. Lamson and Riedel call such a condition a covering condition. as it covers all the cases where a thread needs to wake up. Cost, as we have discussed, is through that too many threads might be awoken. The astute reader might also have noticed we could have used this approach earlier. However, in that case, a better solution was available to us, and thus we used it. In general, if you find your program only works when you change your signals to broadcast, you probably have a bug, fix it. But in cases like the memory allocated above, broadcast may be the most straightforward solution available. We have seen the introduction of another important synchronization parameter beyond lock condition variables. By allowing threads to sleep when some program state is not as desired, CVs enabling us to neatly solve a number of important synchronization problems, including the famous producer consumer problem, as well as current condition. More dramatic concluding sentence would go here, such as he loved Big Brother. Okay, I will end the stream here then. And yeah, I will read the next chapter next stream then. Anyways, see you guys next time. Bye.